Lesson 12.5, Simulations. Our essential question is, what is the difference between experimental and theoretical probability? Our first vocab word is theoretical probability. Theoretical is like the word theory. So theory is what we expect to happen. Theoretical probability, what we expect to happen. So the number of favorable outcomes divided by the total number of outcomes is our theoretical probability. Our experimental probability, or relative frequency, is a little bit different. It's analyzing the results of an experiment. So the number of times an outcome occurs in an experiment divided by the total number of trials in the experiment. So our theoretical probability is what we expect to happen. Our experimental probability is what actually happens after we carry out an experiment. In order to carry out an experiment, you may use what's called a simulation. A simulation is when you use a mathematical model to perform an experiment that is difficult or impractical to perform. So what it means is that you may use a probability model, which is a mathematical model, in order to carry out your experiment. A mathematical model could be a spinner, it could be a coin or more than one coin, it could be a fair die or dice, could be a bag of marbles, etc. One probability mathematical model that you may not have ever used is called a random number generator. That's a function on a graphing calculator that will generate a random number. So for example, if you need there to be 10 possible outcomes for your experiment, and those 10 outcomes are equally likely, you may not want to use a spinner with 10 sections. A coin doesn't have 10 sides, and a regular fair die only has 6 sides. So if you have 10 equally likely outcomes, you might want to use a random number generator. You can control the amount of numbers in your random number generator experiment. So for example, if you need there to be 10 numbers, you can control that you want the calculator to give you a number from 1 to 10. Or if you need 20 or 50 or even 100, you can use the random number generator for any of those. So it's very helpful when the amount of outcomes is larger in your experiment. It's very helpful. Okay, our first experiment, a card is drawn from a deck and replaced 20 times. The results are recorded. So we have the 4 suits: hearts, diamonds, clubs, and spades. Frequencies 5, 7, 6, and 2. Find these experimental probabilities. Probability of a heart. Well, if you look at the results of the experiment, heart is 5, so 5 out of 20 reduces to 1/4. 1/4 of the time that they drew out a card, they got a heart. Next one, not a club. Not a club would be hearts, diamonds, and spades all added together. So that would be 14. 14 out of 20 reduces to 7/10. Probability of a diamond or spade, so if I add those two together, I get 9. So 9 out of 20, and that does not reduce. And then a red card, red cards are hearts and diamonds, so 5 plus 7 is 12 out of 20. And if I divide by 4, that reduces to 3/5. Okay, now, how do these experimental probabilities compare to the theoretical probabilities? Well, what do you expect? If there are 4 suits in the deck, and there are an equal number of cards in each set, so a deck has 52 cards. So there are 13 hearts, 13 diamonds, 13 clubs, and 13 spades. So the probability of drawing a heart theoretically is 13 out of 52, or 1/4. So these probabilities are the same. They're the same for our first one. So what we expected to happen, happened. Not a club. Not a club. There are 3 other suits, so that would be 39 out of 52 cards that are not clubs, or 3/4. That's pretty close, 70% and 75%. So I'm going to say that one is close. Next one, diamond or spade. So that would be 26 out of 52 cards. So that's 1/2. 9/20 is 45%, and 1/2 is 50%. So I'd say that one is close again. And the probability of a red card. A red card would be hearts and diamonds. So 26 out of 52, or half of the deck, would be red cards. And 3/5 is 60%. So that one's not as close as the others. So not as close. 10% away. All right. So that's figuring out our experimental probabilities, figuring out our theoretical, and then comparing the two to see how close they are. Another experiment involves rolling a die. It is rolled 50 times and the results are recorded. Find these experimental probabilities again, and how do they compare to the theoretical. So experimental probability of getting a 3, 14 times out of 50, we got a 3. That reduces to 7/25. And if I turn it into a percent, it's 28%. The probability of rolling a number less than 5. Less than 5 would be 4, 3, 2, and 1. So I have to add all of those together. So 37 out of 50. And that doesn't reduce. It would equal 74% though, because a percent is out of 100. So I'm just doubling the numbers to make it out of 100. The next one, a factor of 6. Factors of 6 would be 1 and 6, 2 and 3. So it would be everything except for the 4 and the 5. So that will give me 37 again. So 74%. And the last one, a 1 or a 4, that would be 13. 13/50 if I add those together, so 26%. All right, now let's compare them to what we would expect. What would we expect if we roll a die 50 times and record the results? Well, there are 6 equally likely outcomes. So if I divide by 6, we would expect 8.3. 8.3 for each one of these. So 8.3 out of 50 is about 16.6%. And that's for each of those numbers. So the probability of getting a 3, we would expect about 16.6% of the time to get a 3, because they're equally likely options. So how does that compare? Not very close. Not very close. The next one, less than a 5, is 4, 3, 2, 1. So if each of those has a 16.6 repeating percent, and I just said 4 different numbers, so that should be about 67% or 66.6%. So that's closer. That's closer than the first one. A factor of 6, again, is the same. So that one's still closer. So those look pretty good. And my last one, a 1 or a 4, so 16.6 repeating. There's 2 of them this time. So 33.3%, about 33%. So again, that's a little bit closer. So not very close on the first one, and then the last 3 were closer. None of them were exactly the same this time, where we had one on the other experiment that was exactly the same. It's not really very common for the experimental and theoretical probabilities to be exactly the same. The more you carry out an experiment, though, you usually do get closer to what you expect, but not always. It's an experiment. Okay, now let's talk about simulations a little bit. So I said you could use a spinner, coin, dice, marbles, or a random number generator on a calculator, what would make sense for each of these situations? So Mr. Foss is giving a multiple choice test with 4 choices, A, B, C, D, for each question. Design a simulation that can be used to estimate the probability of answering each question correctly. Well, if there are 4 choices that are equally likely, I'm feeling like the best option here is going to be a spinner. It's going to be a spinner. And you could have 4 sections that are the same size. You could make them different colors if you wanted to. But I think that a spinner would be the way to go. So A, B, C, and D. All right, my next one. Mr. Foss, again, is giving a true-false test. Design a simulation that can be used to estimate the probability of answering each question correctly. Well, true-false, I would just have to go with the coin, because a coin, true could be heads, false could be tails. It would fit perfectly. There are 2 options, use a coin. The third one, Maddie is a softball pitcher. Last season, 70% of her pitches were strikes. Design a simulation that can be used to estimate the probability that Maddie's next pitch is a strike. So 70% means 70 out of 100 or 7 out of 10. 7 out of 10. So I think, I don't want a spinner with 10 sections. A coin's got 2, a die, fair die has 6. I'm going to use a random number generator on a calculator. And what I'm going to do is not use 100 numbers. I'm just going to use 10. So 1 to 10, and I'm going to say 1 to 7 would be a strike, and then 8 to 10 would be a ball. Because 70% means 7 out of 10, 70 out of 100 or 7 out of 10 are strikes. So 1 through 7, if those numbers appear, that represents a strike. But then 8, 9, and 10, if those numbers appear, that would represent a ball. Okay, you should be able to write a summary now and check with your teacher for your homework assignment.